Okay, this is Math 8, Unit 2, Lesson 9, Side Length Quotients in Similar Triangles. Before, what we learned about was that similar triangles are the images of each other under a sequence of rigid transformations and dilations, and therefore this and a scale factor or made them similar. Okay, so when you have a rigid translation, and dilation, you end up with a scale factor that makes them similar triangles. Okay, so we talked about that before at one point. Let's say, for example, in your warm-up you talked about 2, 3, 4, and 4, 5, 6. Let's say you had a triangle that had a length of 2, a 3, and a 4, and another one that was a 4, a 5, and a 6. And you're talking about whether these are going to be similar or not. One thing we could talk about is that they'd have to have to be an image of each other. There should be a sequence of a rigid translation and dilation there. So looking at a dilation there, to go from a 2 to a 4, that's a dilation times 4. But to go to 4 to 6, 4 times 2 is not 6. 4 times 2 is 8. So it doesn't quite work out there. So these triangles here are not going to be similar to one another, are they? Okay, they share the same scale factor. To go from 2 to 4 is a scale factor of times 2. To go from 4 to 6 is not a scale factor of times 2, it's a scale factor of times 3 over 2. And over here, to go from 3 to 5, that's a scale factor times 5/3. These are all different scale factors, which means these are not going to be similar. It's not going to be a similar triangle. Okay? And this needs to be the same number for all three. If you had 2, it's not going to work. Okay? So it has to be for all three. In activity 2, your teacher assigned you one of 3 columns in the table down here, and your goal was to measure and find out the lengths, not measure, but to look at the lengths of all these sides, the short one, the long one, and what it might be. And so you filled out a little table based upon the measurements that you were given, okay, for the different triangles. And so the length of triangle, we have triangle DEF, GHI, and we have other triangles, and they all have a scale factor. So what we're going to do is we're going to take the scale factor here, and we're going to multiply it as we kind of go down. So 4 times 2 is going to be 8, 5 times 2 would be 10, and 7 times 2 is 14. If we have a scale factor of 3, we do 4 times 3, which is 12, 5 times 3, which is 15, and 7 times 3, which is 21. And then for the half, we have 4 times a half, which is 4 over 2, which is 2. We have 5 times a half, which is either 5 halves or 2.5. And then 7 times a half is 7 over 2, or 3.5. Okay? And so that's where we started off first of all. And then what it asks you to do is to use this information to fill in the next table measurement here to compare the long side, the short side, long side divided by medium side, and so on. And so when we do that, what we find is that the long side for DEF, and you'll need to kind of flip back and forth here, is 14 over 8, okay, which reduces to 7/4. GHI, long to short, was 21 over 12, which again reduces to 7/4. And JKL is, well, same idea here. You end up with a 3.5 over 2. You might think, well, that's less than that. It's actually, each value is half of that. It's the same. So we end up with the same value all the way through. That 1.75 floats all the way down there. Over here, you end up with 7 to 5 for ABC. We have 14 to 10, which reduces to 7/5. We have 21/15, which reduces to 7/5. And then 3.5 over 2.5, which becomes, in this case here, 1.4, which is what all of these are as well. And for our medium side and short side, you have 5/4, 10 over 8, which is 5/4, 15 over 12, which is 5/4, and then 2.5 over 2, which is simply 1.25, which is what you have all the way up there, 1.25. So those are our side lengths there. Got those recorded. and then we have the quotient there for the different side lengths. And what we notice about the quotients is that that quotient stays the same all the way through for all the side lengths. It doesn't change as we're going from one side length to the next, right? So we would say that the quotients of corresponding side lengths in similar triangles are equal, because that stays the same all the way through there. Okay, and you can look at yours compared to your partner's and see what you see in the different triangles there. I just kind of jotted it all there. So now we look at, are you ready for more? Triangles ABC are similar to DEF. So we know they're similar. We want to explain why AB, this one, over BC is equal to DE over this one there. And the reason for that is we have our sides right here. And if we take our sides times a scale factor, that's going to give us our new side, similar to what we talked about before. So let's say, for example, that this was 1, okay, right, and this was a value of 2. So if you took 1 times a scale factor going from 1 to 2 times 2, you end up with a new side length. And that's the idea. So if it's our scale factor times AB, or really we should say AB times the scale factor, is going to be equal to DE. And that's what happens as we go one to the other one. So that scale factor, when you write it this way, BC times scale factor equals EF. The thing with this scale factor right here is a scale factor over scale factor is really equal to 1, which means that it almost, well, it kind of does, it goes away. When you reduce this, reduce it out of there, you're left with just them equal to each other. Okay, let's take a look at this next page. Number 3, you had using side quotients to find lengths of similar triangles. This is a good question. You'll have something similar to this on your test at the end of this unit, so pay attention here. A little tricky, but it's not too bad if you look at how it wants you to solve this. We know, for example, that these are triangles, and what we can tell is that when we look here, 4 and 4, that means that our side lengths are all going to be equal to each other. Like, that's going to be equal. So when I look here, for example, if that's a 4 and that's a 4, and this is 12/5, this one right here would also be 12/5. The reason for that is because they're similar, it's going to be the same straight across from each other. Okay? Good, no problem there. Notice though, how do I go from 6/5 over here, and what's the relationship between 6/5 and 12/5? 6/5 times a number gets you to 12/5. And in this case, we would say 2. So what am I doing here? I'm multiplying this by 2 to come up with 12/5. Okay? So the short side to the long side is multiplied by 2. So if I want to go from the long side to the short side, instead of multiplying by 2, I'll multiply by the reciprocal. So 4 times a half is going to be equal to 2. And that's my length right there. Okay? Now, the same is true over here. If moving from here to here I'm times 2, what is 5 times 2? We would say 10. And if that's a 10, that makes that one also a 10. Okay? And that's all that really has to be done there to show and to find the new angle measurements. Don't make it too complex. You can make it more complex if you wanted to, but there's no need to. All right? So that's what happens right there. So in summary for this lesson today, if we have if two polygons are similar, then the side lengths in one polygon are multiplied by the same scale factor to give the corresponding lengths in the other polygon. So if in this case here, the scale factor is 2. On this one, for what we're looking at here, scale factor is 2, meaning we're going from 3 to 6, so it's times 2. And every one of these should also be times 2. 5 times 2 is 10, 4 times 2 is 8. So we know that our scale factor definitely is 2, and all of our signs are going to correspond to one another, so we're in good shape there. If we take a look then and show that table, this other relationship here, we can take a look and say if I put my measurements here, 4, 3, and then the medium and short side is 4/3. If I did my medium and short side here, 8 to 6, I end up with the same medium and short side ratio there, right? So This is true for all similar polygons. The ratio between two sides in one polygon is the same as the ratio of the corresponding sides in a similar polygon. So if we can figure out that the ratio is going to be, in this case here, 4 to 3, that should also be 4 to 3 there. That's the idea. Can we do it for other ones too? Sure. What if you did 5 to 3? If we did 5 to 3 there, what should that equal? Well, does it equal 10 to 6? That's the question. Sure it does, because our scale factor is 2, so times 2 times 2, 5 times 2 is 10, 3 times 2 is 6, and it shows that they are indeed similar shapes there. You can use that same fact to calculate missing links in similar polygons. For this example here, it says that A prime, B prime, C prime, and ABC are similar. Let's find the length of segment BC. Okay, so knowing this is true, if I can show this relationship between these, then I'm in good shape. Sometimes you can see the relationship here to here. Other times you can't. But what I do see is that I see that the relation between A and B and C, AB and BC is times 2. These are going to be multiplying by 2. If that's the case, then 1.2 times 2 is equal to 2.4 for the length of B prime, C prime. Okay, so look for those other relationships as well to help you solve some of these problems. So we'll pause there, and you're going to work on your homework, and then we'll come back and we'll check it in just a moment. Okay, so here we go, looking at our homework for tonight. Homework for tonight. You have, first of all, two similar triangles. I'm going to go ahead and color these a little bit here because we have a length of 10, which is going to correspond to this length right there of 4. We have the long length of B, which corresponds to this long length of 9. And we also have this length 15, which corresponds to this length A. Okay, so those are my 3 lines for this triangle. We want to find out what A and B are in terms of value, and it does say they're not drawn to scale. That means don't use a ruler to figure it out. Just trust that for argument's sake, they are going to be in a nice proportional relationship. Okay, so here's what we're doing. If we take the red line, what we said before, this value 10 times a scale factor will give me this value here of 4. Okay, this is the basic way to break this down. If I take the 10 multiplied by a scale factor, I can come up with 4 at some point. No problem. If I take this 15 times a scale factor is going to give you the value of A. Okay? And for the B becomes B times the scale factor is going to give you 9. Now there's different ways of writing. So I could change the numbers around a little bit. All right, we could say 4 times the scale factor gives you 10. Because it's reciprocal, I can go either way. So let's figure out from this one first of all. Let's get the scale factor by itself. First of all, I'm going to divide both sides by 10 to find out that my scale factor is 4/10, which is also equal to 2/5. That's my scale factor. All right, so now that I know my scale factor, I can come back to these problems and plug it in. So for 15, I can do 15 times my scale factor 2/5, and that's going to equal A. So 15 times 2/5, this reduces to 1/3, and 3 times 2 is 6, so 6 equals A, and that's where A is going to be right there. For B, we have the value of B times the scale factor, which is 2/5 equals 9. Now, we don't want the B by itself right there, or sorry, we want to get the B by itself, so if I was to multiply by the reciprocal, that would mean I would take 9, B is going to be equal to 9 times the reciprocal, which is 5/2. 5/2 becomes 45/2, which is the same as 22.5 for the value of B. And that's my value of B, 22.5. So we took our original times the scale factor to get our new one. We used that information because we had 2 corresponding lengths given to us to find out our scale factor, Then we use that information to find out the missing values there. So here's triangle ABC, and triangle XYZ, it says, is similar to ABC with a scale factor of 1/4. So we're taking this length and chopping it into fourths. So one of the things I looked at first of all is I said, well, if that's about a half, then a fourth would be about there, right? So that means I'm going to take a fourth and I'm going to cut it in half. Same over here. This length here, about a half is there, so about a fourth is about there. And so if I want to connect the dots, I would say that my XYZ for ABC, XYZ is right here with a scale factor of 1/4 from the original one. So there's where drawing XYZ, where it might be and what it would look like. How do the measures of triangle XYZ compare to triangle ABC? We talked about this the other day. We have one common measurement and one measurement in common, right? So in this case here, angle ZYX is actually congruent and equal to angle CBA. Again, make sure you have the one in the middle be the angle you're talking about there. We also know that because this is going to be going the same length here, I should make it a little more angly, that angle YXZ is going to be congruent to angle BAC. And that's because we did 1/4, 1/4. This angle measurement is also going to be equal to each other. Okay? So that's good there. What are the side lengths of triangle X, Y, and Z? So to solve that then, X, Y, and Z, we know that first of all that this is the easy one to look at here. This length is going to be 1. So we know the side length of YX is going to be equal to 1. That's not too bad to figure out. We're in good shape there. YX is equal to 1. But the other ones, a little bit different, aren't they? Okay. What we want to do is we want to take a look at the scale factor again. So here, if I take my first size, okay, so we have CB, ZY, we would say CB times the scale factor is equal to ZY. Okay, so that's what we're talking about here. This length times the scale factor is going to be equal to that length. Well, CB was 7 times 1/4, our scale factor, gives you 7/4. So the length right here would be 7/4. For this one, we would say that CA times the scale factor equals ZX. Okay, CA was 5, our scale factor is 1/4, so ZX is going to equal 5/4. All right, so those are my new values for the new similar triangle right there. It does say for triangle XYZ in the next part, calculate long side compared to medium side. Okay, so long side to medium side is 7/4 to 1 compared to 7 divided by 4. Either way you end up with 7/4, they're equal. The point being we're wanting to show that those are going to be similar triangles there. Okay. Alrighty. Moving on. It says here that we have two triangles shown are similar. Find the value of DC. Honestly, this one, guys, I got a little stuck myself because I'm not quite sure what it is they want you to do. This would be a great one to ask your teacher about and see if they have. There might be an update that maybe I missed or something. When I look at these parts here, I know these lines, they're going to be similar because we have an angle measurement here is the same. These angles all share the same line, so they're going to be the same there. So we know there's going to be a relationship between these two triangles. It's not on a grid, so I really can't tell what's going on there on my paper. Maybe yours looks a little different, okay? But I'm not sure what's happening exactly. I'm not sure how to get from a 7.5 to a D or from a 9 to a C. I can look here and notice that I have 7.5 times some value. It should give me something. In this case here, if I looked at my Y divided by my 7.5, I know going from there to there, it's equal to 1.2 to go from here to there. 7.5 times 1.2 gets you 9. So I don't know, D times 1.2 is going to be equal to C. That's going to be a true statement, but I don't know what D and C are to figure that out. The book had a solution, but I got a little stuck there. So that one to me was a question mark, and I got to keep on moving. So ask your teacher and see what they say there. The next one says, a diagram shows two nested triangles that share a vertex. Find a center and a scale factor for the dilation that move the larger to smaller. Okay, so we're going to go large to small. We want to find a center of dilation and a scale factor is what we're trying to find here. So our center dilation is going to be right here at point, all right, that's our center, at point -1, 1. We're located right there. Now in terms of our scale factor, I have initially we're at a length of 1, 2, 3, 4, 5. So we're going from 5 down to a length of 1. Okay, so we're reducing from a length of 5 to 1. So my scale factor is going to be 1/5 because I'm making it smaller there. That's the idea. So in this case here, to make this shape go from large to small with a center of dilation being at point -1, 1, that's my center, and my scale factor is going to be 1/5. Same here, 1, 2, 3, 4, 5 down to 1. We're moving it there. Okay, so that's it for today's lesson. Sorry about number 3. Hopefully you get some help from your teacher. Have a great day.